When we think about the global semiconductor shortage, most of us picture empty shelves where PlayStation 5 should be, or car dealerships with sparse inventory. But high above Earth, a far more consequential drama is unfolding. The space industry, responsible for everything from GPS navigation to weather forecasting and global communications, faces an unprecedented challenge as it struggles to secure the specialized chips needed for satellites. Today, we'll explore how this silent crisis is fundamentally changing how we build, launch, and operate technology in space, and why these changes may permanently alter humanity's relationship with the cosmos. The space industry's semiconductor problem goes far beyond what we see in consumer markets. Satellites don't just need any chips, they need radiation-hardened semiconductors specifically designed to withstand the harsh environment of space, where cosmic rays and solar radiation can easily fry standard electronics. These specialized components come from only a handful of manufacturing facilities worldwide. Unlike smartphone makers who can leverage massive purchasing power, satellite producers often find themselves at the back of the queue for these critical components. Recent reports show satellite manufacturers facing staggering delays of 18 to 24 months for these specialized chips, and there's simply no easy substitute. You can't just swap in commercial-grade alternatives and expect a satellite to survive in orbit. This vulnerability has become what the European Space Agency recently called the most significant supply chain challenge since the early days of the space age, putting semiconductor availability on par with rocket technology in terms of strategic importance. These shortages are causing tangible disruptions across the industry. Just last week, satellite operator Eutelsat announced that its next-generation telecommunications satellite deployment has been pushed back by a staggering 16 months, specifically due to component shortages. Even SpaceX, with all its resources and manufacturing prowess, hasn't been immune. The company has modified its Starlink satellite designs 3 times in the past year alone, not for performance improvements, but simply to accommodate whatever chips they could get their hands on. While this approach has kept production lines moving, industry insiders suggest these compromises have affected power efficiency and signal processing capabilities. The specific components facing the most severe shortages include microcontrollers, field programmable gate arrays, FPGAs, and radiation-hardened memory, all essential for satellite operation. For critical satellites supporting national security, weather forecasting, and global communications, these aren't mere inconveniences but strategic vulnerabilities that affect services millions rely on daily. The semiconductor shortage has accelerated a profound shift toward national self-reliance in space technology. Countries increasingly view satellite manufacturing capability not just as an industrial asset, but as a matter of national security. Just yesterday, the European Space Agency announced a massive €1.8 billion initiative to establish a European supply chain for space-grade semiconductors, reducing dependence on US and Asian suppliers. China has similarly accelerated its domestic production capabilities, with the China Aerospace Science and Technology Corporation opening a new facility in Shenzhen dedicated specifically to radiation-hardened microprocessors. The United States has responded through the CHIPS Act, which allocates specific funding for defense and space-related semiconductor manufacturing. This fragmentation represents a significant departure from the previous 2 decades of increasing globalization in space technology. As national space ecosystems become more self-contained, we risk developing incompatible technological standards. Some analysts warn of a balkanization of space technology that could increase costs and reduce innovation. Others see opportunity in this diversity, suggesting that technological competition might accelerate advancement while creating redundancies that strengthen humanity's overall space infrastructure. Facing persistent hardware constraints, the space industry is undergoing a fundamental philosophical shift toward software flexibility. The concept of software-defined satellites, where capabilities can be modified through updates rather than hardware replacements, has gained extraordinary traction. Just this month, Airbus Defence and Space revealed that their latest generation of telecommunications satellites incorporates reprogrammable payload technology that can adapt to changing mission requirements without physical component changes. This represents a complete reversal from traditional satellite design, where dedicated hardware was built for specific functions. Now, The emphasis is on general-purpose computing platforms that can be reconfigured throughout their operational lifespan. Lockheed Martin's latest GPS-3 satellites exemplify this trend, with an astonishing 70% of functionality now implemented in software compared to just 20% in previous generations. This software-defined approach offers tremendous resilience against component shortages by allowing manufacturers to use a wider range of semiconductor options. When specific chips are unavailable, alternatives can be employed with software compensating for hardware differences. The flexibility extends to in-orbit operations as well, allowing satellites to be repurposed for entirely new missions as market demands change. Industry experts now predict that by 2030, nearly all commercial satellites will incorporate some degree of software-defined functionality, one of the most significant technological pivots in the industry's history. The semiconductor shortage has reshuffled the competitive landscape of the space industry, creating unexpected winners and losers. Smaller satellite manufacturers with less purchasing power have been disproportionately affected, with several startups facing existential threats. Swarm Technologies, which was developing a miniature satellite constellation for IoT applications, was acquired by SpaceX last year, partly due to supply chain difficulties they couldn't overcome independently. Conversely, companies specializing in satellite refurbishment and lifetime extension have seen surging demand for their services. Northrop Grumman's Mission Extension Vehicle Service, which can extend the operational life of existing satellites, has secured 5 new contracts in 2023 alone. Operators are increasingly seeking to maximize the utility of satellites already in orbit rather than launching replacements they can't build due to component shortages. End quote. The economics of satellite design have also shifted dramatically, with increased emphasis on longevity over cutting-edge capabilities. Industry analysts note that geostationary satellites' average planned operational lifespan has increased from 15 to over 20 years since 2021, reflecting a more conservative approach to fleet management in uncertain supply conditions. This represents a fundamental shift in how space assets are valued and utilized. The semiconductor shortage has forced engineers to revisit fundamental assumptions about satellite design. Rather than simply waiting for supply chains to normalize, companies are developing innovative workarounds that may permanently change spacecraft architecture. One approach gaining traction is the implementation of radiation-tolerant commercial off-the-shelf (COTS) components with additional shielding and redundancy systems, rather than traditional radiation-hardened chips. While this requires more complex fault detection and recovery systems, it enables access to a much broader range of components. Another innovation involves distributed computing architectures that spread processing tasks across multiple smaller, more readily available chips rather than relying on a few specialized processors. This approach not only addresses supply constraints but also provides greater resilience against single-point failures. Some manufacturers have even begun implementing hybrid analog-digital systems for certain functions, reducing dependence on advanced digital components for applications where analog solutions can provide adequate performance. These engineering adaptations represent more than temporary fixes, they're fundamentally changing how engineers think about spacecraft design, potentially leading to more robust and adaptable systems even after supply constraints ease. The semiconductor shortage has elevated space technology to an unprecedented level of geopolitical significance. Access to radiation-hardened chips has become a form of strategic leverage in international relations. Countries with domestic production capabilities are increasingly reluctant to export these technologies, viewing them as national security assets rather than commercial products. This has created new diplomatic tensions, with space technology export controls becoming a contentious issue in international trade negotiations. The United States has tightened restrictions on space-grade semiconductor exports to China, while European nations have accelerated efforts to develop sovereign capabilities independent of both American and Asian suppliers. This technological nationalism extends beyond manufacturing to intellectual property and design expertise. Universities and research institutions are facing new restrictions on international collaboration in radiation-hardened semiconductor research, reversing decades of open scientific exchange in space technology development. Some experts warn that this fragmentation could lead to technological divergence, with different regions developing incompatible approaches to space systems. Others argue that competition will ultimately accelerate innovation, though at the cost of duplicated efforts and resources. What's clear is that space-grade semiconductors have moved from a niche technical concern to a central element of national technology strategy, with implications that extend far beyond the space industry itself. Perhaps nowhere is the impact of the semiconductor shortage more evident than in the evolution of satellite constellations. These networks of coordinated satellites, like SpaceX's Starlink or OneWeb, were originally conceived around rapid iteration and regular technology refreshes. The vision was to continuously launch improved satellites as technology advanced, creating ever more capable networks. The component shortage has forced a dramatic rethinking of this approach. Constellation operators are now developing more modular designs where only specific subsystems need replacement rather than entire satellites. They're also implementing more sophisticated fleet management strategies, where older satellites are assigned less demanding tasks while newer ones handle more processing-intensive functions. This has led to what industry insiders call heterogeneous constellations, networks comprised of different satellite generations working in coordination, rather than uniform fleets. Software updates have become increasingly important for extending the utility of existing satellites, with operators investing heavily in the ability to reconfigure orbiting hardware. These adaptations may ultimately lead to more sustainable approaches to space utilization, with longer-lasting assets and more efficient use of orbital resources. What began as a response to supply chain constraints could evolve into a more mature model for managing large-scale space infrastructure. The ability to produce radiation-hardened semiconductors has emerged as a defining capability in the modern space race. Unlike the original space race focused on launch vehicles and crewed missions, this competition centers on the microscopic components that enable sophisticated satellite functions. The manufacturing process for these specialized chips is extraordinarily complex, requiring specialized facilities, equipment, and expertise that few organizations possess. Traditional radiation hardening techniques involve using specialized materials like silicon on insulator substrates, wider transistor gates, and redundant circuit designs that can withstand particle strikes. These processes typically lag several generations behind commercial semiconductor technology in terms of miniaturization and performance. Now, under pressure from shortages, both government agencies and private companies are investing in new approaches. The Defense Advanced Research Projects Agency, DARPA, has launched a program exploring advanced packaging techniques that could protect commercial-grade chips against radiation effects. Meanwhile, private companies like BAE Systems and Microchip Technology are expanding their radiation-hardened manufacturing capacity with new facilities. The race extends beyond traditional radiation hardening to include novel approaches like self-healing circuits and radiation-aware software that can detect and recover from radiation-induced errors. These innovations could eventually bridge the performance gap between radiation-hardened and commercial semiconductors, with implications that extend beyond satellites to nuclear facilities, medical equipment, and other radiation-exposed applications. What began as a supply chain disruption has evolved into a catalyst for fundamental change across the space industry. The semiconductor shortage has forced a re-evaluation of long-held assumptions about satellite design, manufacturing, and operations. The initial panic has given way to strategic adaptation, with companies developing new technologies and business models that may outlast the crisis itself. The shift toward software-defined satellites represents more than a temporary workaround. It's a fundamental reimagining of space assets as flexible platforms rather than fixed-function devices. Similarly, the renewed focus on extending satellite lifespans and repurposing existing hardware reflects a more mature, sustainable approach to space utilization. The nationalization of space-grade semiconductor supply chains, while concerning from a global cooperation perspective, is driving investment and innovation that might not have occurred otherwise. As one industry executive recently noted, we've compressed a decade of architectural evolution into 3 years of crisis response. The space industry that emerges from this period will likely be more resilient, more software-oriented, and more focused on sustainability than before. Systems will be designed with supply chain uncertainty as a core assumption rather than an exception. While the semiconductor shortage has undoubtedly caused significant disruption and delay to important space missions, It may ultimately be remembered not just as a period of constraint, but as the catalyst that pushed the industry toward greater technological maturity and operational sophistication. The global semiconductor shortage has revealed both the vulnerability and adaptability of humanity's space infrastructure. What began as a supply chain crisis has catalyzed a profound transformation in how we conceptualize, build, and operate satellites. The shift toward software-defined systems, the renewed emphasis on longevity over constant replacement, and the strategic nationalization of critical component manufacturing are reshaping the industry's fundamental architecture. While these changes were born from necessity, they may ultimately create a more resilient, sustainable approach to space technology. As nations and companies adapt to these constraints, we're witnessing the emergence of new business models, engineering paradigms, and geopolitical considerations that will influence space development for decades to come. The semiconductor shortage, paradoxically, may be remembered as the crisis that pushed the space industry toward greater technological maturity, a difficult but necessary evolution that strengthened humanity's long-term relationship with the cosmos. In our rush to explore and utilize space, we've been forced to slow down and reconsider our approach, potentially setting the foundation for more thoughtful, sustainable expansion beyond Earth. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.